Alright, welcome to your next data structures video. In this video we're going to talk about pointers, but it's going to be a different focus from what we talked about in CSE 222. If you go back to that playlist, we talked about pointers in terms of the mechanics of pointers, and we used a little box with pieces of paper inside to represent memory locations and their contents. If you don't remember the details of that video, I suggest you go back and watch that as a refresher, because we're going to be using the idea of pointers today to start building up some data structures working towards what's called a linked list. And I'd like to begin with the notion of a structure in C. So let's put together some C code. I'll just call this main1.c. And remember, in C we have variable types. We have integers, we have characters, we have doubles, and so on. But we can create new types of variables using what we call a structure statement. So I can say struct my data, and I can define a new type of variable called a my data that can contain multiple pieces of information. So for example, it might contain some integer which represents the time, and some character which represents a code, and maybe a name which is 120 characters, and maybe an index which is an integer. And so I write a statement like this: structure, the name of my structure, and then inside curly brackets each of the fields that are going to be part of my structure. So this structure has 4 fields: time, code, name, and index. And very important, at the end of a structure definition, you got to have this semicolon. If you don't, you get about 3 billion errors when you compile, and it's all just from one missing semicolon. So let's use this structure. Let's make a main program. And I can do something like this: struct my data x. So x is a type of variable that we call a structure. It's a structure of type my data. And I can do something like this: x.time equals 730. X.index equals 12. X.code equals quote t. And I could do something like copy into x.name the name Nick. So at this point, I have a variable named x which contains all 4 of these fields. It's a single variable, but it's got all 4 of those pieces of information in it. And so I can examine it by saying something like just a printf statement. Let's just say time equals %d, index equals %d, name equals %s, and code equals %c. And I'm going to specify the fields that I want to print. So if I want to access the time field of something called x, I say x period time, and then x period index, x period name, and x period code. Commas a little nicer. Alright, so x is the variable itself, but x.time is the time field of that variable. And so this by itself should let me print out that information that I've stored in here. So let me go ahead and compile this. And I forgot to include string.h, so I'll go ahead and put that in because I'm using string copy. And then recompile. And now if I run main1, it tells me, the values that I saved in my structure. So that's convenient if we have multiple pieces of data that aren't just randomly, chosen pieces of data, but that somehow belong together. For example, if I was recording student information, I might have a structure called student info, and it can contain the student's name, their student ID, what year they are in school, what their major is, other information about them, and so on and so forth. So, I've got random stuff in here. I don't know what a timer, a code, or an index is, but it's just an example, right? So one advantage of having a structure like this is it makes it easier if we're going to process this data inside a function. We could just pass this single variable x instead of passing 4 variables, time code, name, index, and so on. So let's try that. Let's make a function, and let's call it print data, and we'll just say this is a function that prints the data. And let's define our function. So this is void print data. It takes a single argument, which is x in this case. What is x? It's a struct my data. Struct my data. So I'm going to say struct my data, and whatever I want to call the argument. I could call it x, but let me just call it something like arg, so we don't think x is magic. And let me do this. I'm making a mess of my line here. That's okay. It's good VI practice. All right. So I have my function. It's going to take a struct my data, and then it's just going to print out the contents of that argument. And let me prototype my function. So we're used to putting our function prototypes at the very top of our code, and that's usually a good policy. But in this case, if I do that, I'm going to get some compile errors. And the main problem here is that my prototype talks about something called a struct my data, but struct my data isn't defined until down here. So we're going to want to move this down below the structure definition, so that when we say, hey, here's a prototype for a function that takes a struct my data, the compiler knows what that is. So now we can compile that, and if we run it, it does the same thing as before. But now if I wanted to do something like this, let's say I want to change x. So let's say x dot time equals 99. And then I could reprint my data by just calling the print function again. And I'm just going to reuse this code, but it should print out the same thing, except the time value will now be 99. So if I run this, the first time was 730, the second time was 99. So we can pass around multiple pieces of data with just this single symbol x. And that's a big advantage. It's going to make our code cleaner. It's going to make it less error prone because we don't have to remember the order in which things are passed. But it's also going to logically make more sense because we're going to be grouping these things together inside these structures. So if I have 5 pieces of data that are related to each other, I can define a structure that specifies that relationship, and then we can just use that structure. Now, for reasons that will become clear in a few minutes, it's more common that instead of actually passing the structure itself, we're going to pass the address of the structure. And so down here, instead of calling print data x, I would call print data ampersand x. Now, if I'm going to do that, I have to change my function prototype and say, hey, my argument is a pointer to a my data. And then I have to do that in the function definition itself. And now arg.time is not going to work because arg is no longer a structure. If I try to compile this, right, I'm going to get errors saying, hey, this is a pointer. Did you mean to use this? So we'll come back and we'll use this in a minute. But right now, here's what you want to think about. Arg is a pointer. So arg is a struct my data pointer. So if I say star arg, what is that? That is a struct my data. And struct my data contains fields such as time or code. So if we want to access these fields in this pointer to a structure, we have to use something a little goofy looking like this. And I'm adding the parentheses for clarity so that we know that first we're going to dereference arg, and then the thing that we've dereferenced, the structure, we're going to pull off the appropriate field from that structure. So now this should compile fine, and when I run it, it works exactly like before. But when we had this error earlier, it gave us a little hint in the error message which said, did you mean to use -sign greater than, this thing that looks like an arrow? And yes, that is what we want to use. So here's the deal. We can say *arg.time, but there's a shortcut in C for writing this, which is to simply say arg arrow time. And if we want to say *arg.code, we can say arg arrow code. And you'll figure out a way to interpret this when you see it, but to me, this says, you know, arg is a pointer, go to the thing it points to and pull off the code piece. Arg is a pointer, follow it to the thing it points to, and then pull off the time piece. So now I can write this line a little cleaner, and I can just say arg arrow time, arg arrow index, arg arrow name, and arg arrow code. And I can put a comment here saying that's the same as this thing, but we're going to write it like this. So if we compile that, that compiles and runs, and it works exactly the same. But when you're writing code using pointers to structures, you always want to do it like this. Unless for some reason you're told to do differently, don't do it like this. Right? This would be considered, you know, not very professional. And if you did this like in a job interview, for example, they would wonder, well, do you know about, you know, using this? But what's the real difference here? There's not a whole lot of difference in typing this or this. But suppose that we have a structure which contains a pointer to another structure. So, and if this doesn't make sense, it will down the road. So let's look at a struct stuff. And suppose it contains a struct more x. It would probably have other stuff. And suppose I have something called a struct stuff star data. And suppose the structure more has an integer x and an integer y and an integer z. Alright, so what have we got going on here? We've got a variable named data which points to one of these structures, which contains a pointer to a structure which contains fields x, y, and z. So if I wanted to get the x field associated with this, or let's say the z field associated with this structure being pointed to by the data, I could say star data that points to the struct stuff, and then I could say dot x, which is the pointer to a more, and then I could say star all of that, and then I could say dot z, and that would get me to this field right here. But with the arrow notation, I could simply say data arrow x arrow z. And what does the arrow mean? Take data, it's pointing to something. Go to the thing it points to, right, which is one of these structures, and grab the x field. The x field is a pointer. Follow it to the thing that it points to, which is a more structure, and grab the z field. And so we'll be able to chain these things together and say, you know, start at data, go to what it points to, go to what that points to, grab the z field. And it's going to make a lot more sense than trying to do this. So that's kind of a teaser. When you get into the problems, you'll actually do this in some examples. It'll make more sense there. But that's the mechanics of how we're going to work with pointers to structures. And that's pretty much what we're going to do the rest of the course. Most of our structures, we'll pass them around by address, like this, rather than by just passing the bare structure itself. So the next point is, when we're writing our code, we can define variables. For example, I've defined a variable x, which is a struct MyData, and I can pass the address of it with an ampersand, or I could just pass it as an x if I don't want to deal with pointers. And that's fine. That's stuff that we've been doing in 224, a little bit in 121. Where this idea gets really powerful is when we start actually creating our variables not in our source code, but directly in the memory of the computer while the program is running. And so as our program is executing, it's going to start creating new, in this case, struct MyDatas. And if we look at the source code, we may not actually have a struct MyData, or we may have one variable x of that type. But as the program is running, it could create 2 or 5 or 10 or 100 or 1,000 or 1,000,000 different struct MyDatas all throughout the memory of the machine. And so this is the idea of runtime memory allocation. Right? When we do this, we're creating variables at compile time. When the program is compiled and linked and turned into an executable program, space is made available for this structure, and our structure is always going to be sitting in that designated space. But with a runtime or a dynamic memory allocation, as the program executes, we create these structures. So to do that, we're going to have to use a malloc statement. And if you look at malloc, it comes from standardlib.h. And it's a pretty simple function to use. You simply tell it how many bytes of memory you need, and it returns a pointer to the first of a block of memory that's at least as big as you requested. So if I need to store 10 bytes, I could say malloc parentheses 10, and it should return a memory address, a pointer to somewhere in memory that has at least 10 bytes of free memory that I can use for anything I want, and nobody else is going to be able to access as long as I'm using it. So malloc is going to be used heavily. It's the way that we're going to find memory and start using it at runtime, right, as our program is executing. And this is the real reason why we want to use pointers to structures instead of just structures, because malloc gives us back a pointer. So here's how we can do this with malloc. I'm going to say struct MyData star x. So x is a pointer to a structure. And we need to point somewhere usable in memory. So we can say x equals malloc. And we need to tell malloc how many bytes of memory we want. Well, I don't know. For now, I'm just going to say 100 should be plenty. Actually, it's not. Let's make it 500. Now, you would never do this in an actual program, but this is just an example. We're going to allocate 500 bytes of memory. And x should be, a pointer to that much memory. So now, when I want to store something in the time field, remember x is a pointer, so I have to say follow what it's pointing to and set the time field equal to that. Do the same thing for this field and that field. And then here I'm going to say x arrow name, right? And x arrow name is going to refer to, hey, follow name, it's a pointer to a MyData. Go into that MyData, look at the field called name. That's a block of 120 characters. Let's copy Nick into that. And now when I try to print my data, I don't pass ampersand x, I just pass x. And then if I want to change x's time, I say x arrow time equals 99, and I just pass x. Now my function doesn't change at all. I'm still getting a pointer to a MyData. The only difference is that when I start running my program, my data x in some sense doesn't exist. X is declared to be a pointer to a MyData, but it's not initialized. And if I don't do this malloc, I'll probably segfault. We'll try that in a minute. But right now I should get a block of memory, and this program should do exactly the same thing as it did before. I need to include standard lib, because that's where malloc comes from. Right, and so we're still in business, working exactly the same as before. All right, so let's play with this. Suppose I don't do my malloc. Right, I get a segfault. Now, why am I getting a segfault? Well, x is a pointer. Let's see what x is pointing to. And I'm going to use a %p to say treat x as a pointer. So if this was a 32-bit machine, I could just print x out as an integer, but it's best practice if you're going to print a pointer, use %p, and it'll put it in you know, a nice hex notation and so on and so forth. So if we run this, it says x points to location parentheses nil. This means x is equal to 0. If I printed it as a decimal, it would show me that it's a 0, because I haven't initialized it yet. And remember, on our systems, memory location 0 is reserved. It's set up in the memory management system to deliberately be a non-accessible memory location. That's so that if we do something like forget to initialize a pointer, it'll throw a segfault instead of just writing into some random location in memory. So let's put the malloc back in place, and let's see what our pointer looks like. And you can see x points to location 55B, 66C, 29C, 2A0. That was the location that malloc gave me when I asked for 500 bytes of memory. Now if I run this again, I get a different location. Right, I had 55B, 66C, now I've got 563 AEF. And if I run it again, I get it 560 0F0. So we can't easily predict where malloc is going to decide to let us store things in memory. It's going to give us a more or less random location, and that's actually kind of useful from a security perspective. But it also means that, you know, when we have bugs related to code that's allocating memory at runtime, they can be hard to find, because sometimes your code will fail and then you run it again and it'll work. And you run it again and it works, and then the next time you run it, it fails. And so if you start seeing unpredictability in your code, there's probably a problem with your pointers. And we're going to play around in a future class with using GDB to dig into code that uses pointers. Alright, so a couple of other things. Let's get rid of this notion of allocating 500 bytes. That's a random number I picked, but we really don't want to do that. Now, we could add this up. We could say time is an integer, that's 4 bytes. This is 5, this is 120, that's 125. And another 4 for an int, that's 129 bytes. But don't do that, right? The correct way to choose how many bytes to allocate is to use the sizeof statement. So you say sizeof, and then inside these parentheses you say the type of thing you want to allocate space for. So what type of thing are we allocating space for? A struct MyData. So I'm going to put a comment here, only put the type of a variable in the argument to my size. So if I do this, I can recompile and run it, and it still works great. But we can get into trouble if we start putting variable names in here instead of types of variables. And let me show you why that is. So let's just print out size of struct MyData. And I'm pretty sure this %d is going to complain because it should be a long or something like that. But let me just cast this to an int because it's not going to be a big number. So let's just print out size of struct my data, and let's see what that's equal to by using a print statement. And it tells me size of my data is 132 bytes. And remember, we added up the size of each field and we got 129. But malloc is never going to allocate 129 bytes. It's going to allocate usually a multiple of 8 on this system. Depends on your operating system, the size of your CPU, and so on. But it's going to allocate extra space in general because things work better if certain things fall on 4 or 8 byte boundaries. We would never want an integer to start at an address that's odd, for example. It will destroy the performance of the CPU. So malloc knows how to allocate space, but sizeof is a compile thing, right? Sizeof is determined by the compiler. And so here's where we can get into problems. Let's say sizeof, and we know that x is a struct my data. So let's print out size of x. And I'm just going to say don't do this. Alright, print out size of x is %d, and we'll just print out size of x. And guess what it's going to return? It's going to say size of x is 8. So here's a case where if we had allocated space by mallocing size of struct or size of x instead of the type of thing that x is, we would end up only allocating 8 bytes. And when we start trying to use things that, are 100 bytes past the beginning of that block, we may get a seg fault, or we may simply be writing on other parts of memory that we shouldn't be writing on. And so this is where you can start to get kind of crazy behavior from your program that sometimes does one thing, sometimes does another thing. So when you say size of, use the type of a variable. Don't use the name of a variable. This is a little bit of a ongoing war if you go online. Some people will swear you should do the other way. I will tell you that for what we're going to be doing in this course, if you stick to putting in the type of a variable instead of a name, you should be okay. If you put in the name of a variable, there's a good chance that you're going to end up getting bizarre bugs in your code. Alright, so that's how we use malloc. So the next thing to talk about is memory leaks. So we're allocating memory in here, and then we're storing some information and so on. And you notice that when I was printing this location, so let me put this print statement back in. Let me take out these. And every time I run this, I get a different location in memory that it's storing my information in. So you might wonder, what happens after my program exits? Is my information still in that location in memory? And if so, is that a problem? Does that memory get used forever, or does it somehow get reclaimed? So on Linux, the answer is yes, your data may still be in that location, but that location will be marked as being available. In other words, the operating system will know that the person who malloced it no longer needs access to it, and it's possible that some other process will eventually start using that memory location. So how do we know if we've got memory that's still being allocated when we exit the program? We can use something called valgrind. And to use valgrind, you just say valgrind, and then you run your program the way you normally would. And it runs your program. It gives you the output from your program. And then at the end, it gives you what's called a heap summary. So the heap is the thing that malloc gets memory from. And it says, in use at exit, 132 bytes in one block. So I've allocated one block of memory that was 132 bytes, and it is still in use when I'm exiting my program. And so it says I have a memory leak. That means you've got memory that you've allocated but haven't released. And I've definitely lost 132 bytes of memory in one block. All right, and you can add switches to valgrind. You can say leak check equals full and get a lot of information from that. You can also compile with a -G switch and get more information from the symbolic information stored in your executable. But the main punchline here is, hey, we've got a memory leak, right? So how do we deal with this? Well, it's really simple. If you remember when we looked at malloc, this is the function we use to allocate memory. The next thing described in the synopsis is a function called free. And it says the free function frees the memory allocated by malloc, or any of these other versions of malloc. Right? So malloc allocates memory, free releases memory. All right. By the way, I am only going to talk about malloc in this course. There are other things you can use, calloc, realloc, and so on. I'm only going to use malloc. I'm going to use malloc every time that I want to allocate memory, and I'm going to ask you to stick with malloc. It's going to simplify your life, and if you're working on code on your own, you want to explore reallocation and so on, you can play with these others. We're just going to stick with malloc and free. Keep things simple. So free, you give it the address of the beginning of the memory block that you want to free. So let me go into here, and after I'm done using X, let's free it. So I'm just going to say free X. And that's all it takes. So now when I compile this and I run it, it looks exactly the same, but when I valgrind it, now I get a different heap summary. It says in use at exit 0 bytes and 0 blocks. And here's what you want. All heap blocks were freed. No leaks are possible. That means you're not going to lose any points for having memory leaks. So the whole idea is when you're done with a block of memory, call free, and that releases it. Then, as I said, in Linux, right, when your program exits, the memory that you allocated is automatically freed. But if you had a program that never exited, like you were running a server that was just going to run and run and run, and remember, you know, it's not unusual for servers to stay up. You know, our Linux server's been up for half a year now. If your program is leaking a little bit of memory every few seconds and it runs for half a year, you're going to start running out of memory. So it's good practice, and it's mandatory practice in this class, that when you're done with memory you've allocated, you want to free it. And if you're using that memory until the end of the program, and then at the end of the program you're about to exit, you still want to free that memory. Even though it'll be freed for you, free it yourself. All right, so that's memory allocation and memory leaks. Valgrind for looking for memory leaks, and free to release memory that you've allocated. All right, so the last topic we want to talk about is a particular type of structure that we're going to use either directly or variations of this in most of what we do this quarter. And so we're going to create something that we can think of visually as looking like this. I'm going to call this a node. It's really going to be a struct called node. And the nodes I'm going to define are going to have two fields. And for simplicity, this first field is going to be an int, and the second field is going to be a pointer. And what's cool about this is that the thing that this points to is also going to be a node. And that node will contain perhaps a different integer and a pointer, and that pointer will point to another node which could contain a third integer. And so we're going to take these nodes and we're going to link them together into a list. And this is going to create something called a linked list. Alright, so let's write some code and play around with this. So I'll just make a main.c. So we're going to have to do some malloc, so I'm going to include standard lib. And I'll just call my structure a node. And I'll call this first field data. And my second field is going to be a pointer to a struct node. And I'm going to call it next. So my node will actually look like this. It's going to have an integer field called data, and it's going to have a pointer which is called next, and that's going to point to a struct node. So this thing, we can think of this as a struct node. And this might look circular. We might worry that, this is going to point to itself, and when we go inside, we're going to find a pointer to itself. But this is just a pointer. This is a memory location, right? And even though this whole thing, we're treating it as a single structure that we call a node, the fact that we have a memory address in here does not cause any problems at all. It happens to be a memory address which is pointing to a possibly different struct node, but that doesn't matter. It's just a memory address. It's a 16 or 32 or 64-bit number, depending on our CPU. Just like data is a number, it's an integer. So we've got a bunch of data here, we got a bunch of data here. We can interpret this as the address of a struct node, but it's not actually self-referential. So we're not going to get any problems with a compiler. Now, if I said that this next field was actually a struct node, that would be a problem. Because that would say inside this node I have a structure, and inside that structure I have a data field and I have a structure of type struct node, and inside that field I have a data field and a struct node, and that would be recursive, and that would get the compiler upset. But since we're going to have a pointer to a struct node, no problem. Alright, so let's make a few struct nodes. I'll call them N1, N2, and N3. Those are each going to be pointers. And let's allocate memory for these. So we're going to malloc sizeof, and remember we want to use the size of the thing that we are going to store in this block of memory, and the thing we're going to store is a struct node. And we'll do that for N1, N2, and N3. And then let's save some data in here. So I can say N1 data equals 10, N2 data equals 20, N3 data equals 30. Alright, so what am I building in memory here? I've got 3 of these struct nodes. This is N1, N2, N3. This has got a 10, this has got a 20, this has got a 30. The next fields, who knows what's in there? I haven't specified yet, so they're probably going to have zeros in them, but they could have random values in there. But let's make these values something interesting. So let's make N1 point to N2. So what I want to do is take this pointer, and I'm usually going to use my curved arrows like this, and I want it to point to this block N2. Okay, how am I going to do that? I want to specify a value for this field, which is called next. Now N1 is a pointer to a struct node. So I want to take N1, I want to follow it to the thing that it's pointing to, and then I want to hit the next field. So N1 arrow next, that's this box right here. And what do I want it to be equal to? I don't want it to be equal to 20. I want it to be equal to the address of this node. Well, what is the address of this node? Where is the location in memory where n2 is stored? That's the value of n2, right? n2 came from malloc. n2 is the address of that node, n2. So I want to say n1 next equals n2. And I'll put a comment here. n2 is the address of node n2. And so I'm copying that address into n1 arrow next, which is this box down here. So similarly, I could say n2 next equals n3. And I could say n1 next, n3 next equals, I don't know, I could have it point back to n1. So now I'm building what we'll eventually call a circular linked list that looks like this. So let's look at the data. Okay, so here's what I can do. I can say struct node temp. This is just a temporary variable. And I can say temp equals n1. So I'm making this variable temp, which points to this first block of memory. Now I did not do a malloc statement for temp because I don't need more memory from the system. My goal is not to create a new struct node, but simply to have temp point to this already existing struct node that was allocated up here. So I can just declare temp to be a struct node pointer, and then set temp equal to n1. And let's print the data inside temp. So temp data equals %d. And let's print temp data. So when I do this, I've simply made temp point to n1. Temp data should print out a 10. So let's make sure that we're in the realm of reason so far. Let's compile that and run it, and temp data is equal to 10. Alright, now we're going to do something really crazy. We're going to take this variable temp and we're going to change it so that it points to the next node in our list, n2. So how are we going to do that? How do we find n2? Well, n2 is stored right here. So we're going to do the following statement. We're going to say temp equals temp arrow next. Alright, this is the whole course right here. What does this mean? Temp is the address of this node. So follow that address to the thing it's pointing to. That's this node. Pick up the next field. What is in there? The address of n2. Set temp equal to the address of n2. This one statement changes temp to point right there. And now if I print temp arrow data, I should print out the 20. So let's do this. Temp equals temp arrow next. Move to the next node. And then let's print out the value of that next node. So if I run this, temp data was 10, and then temp data was 20. Well, I can do this a bunch of times. I can print out temp data and then move to the next node. Print out temp data, move to the next node. Print out temp data, move to the next node, and so on. And each time I do this, when I say temp equals temp next, whatever temp is pointing to, this statement should change it to point to the next thing. And when temp is pointing to n3 and I say temp equals temp next, what does it do? Follow temp to the thing it's pointing to, that's this. Pick up the next field, that's this. What's in here? the address of N1, that's going to make temp point back to N1. So if I compile this and I run it, it's going through our list. Temp data was 10, 20, 30, 10, 20, 30, 10, 20, 30. So we have a circular list. And so this is an example of a dynamically created memory structure. It's a structure we built up inside the memory of the system. And it did not exist when our program started executing. When our program began executing, all we had was 3 pointers to nodes. But we didn't initialize these at compile time. So we used these malloc statements to find memory that we could use to store the contents of these 3 structures, N1, 2, and 3. And then we put in some data, and then we linked them together into this circular list. And once we do that, we can move through this list by using this temporary pointer, initializing it to N1 and just marching down the list. So what's the advantage of this, right? Why couldn't we just have 3 structures called N1, N2, and N3 and not bother with malloc? Because we did 3 malloc statements, we did 3 assignment statements here, we did 3 statements linking them together, but that was just for clarity. We could have a loop that just each time we go through the loop calls malloc, takes a data value and assigns it in the data field and changes the pointer to point to the next node in the list. And we can build this list up at runtime. And if somebody were to provide, 1,000 pieces of data, we could loop 1,000 times, and each time create another node in this list and link it in with the previous list. And nowhere in our code would we have a variable that pointed to each of those nodes. Right? We would simply have a variable pointing to the first node, and then we would follow that by using node arrow next, and so on to move down the list. So that's where we're heading with this. This is really just a first introduction, and the practice problems will let you get your feet wet and play around with this and start working with some of the mechanics of this, but also trying to connect it visually or graphically to something like this. And you're going to want to draw a lot of pictures in this class. When you're working with dynamic memory and you're creating lists or trees or structures like that, draw pictures. And find a way to draw pictures that make sense to you. It's different for each person. It took me about 2 weeks playing with linked lists before I settled on this way of representing what's going on. But there's other ways to do it. And it's highly personal. But find a way that makes sense to you. Experiment. And once you have a way to visually represent on paper what's going on, then writing this code becomes pretty easy. Because you use the pictures that you draw to know what you want to do, and you just write statements in C to tell the compiler, hey, give me some code that does that. So being able to link this to some kind of visual representation is going to be important, and so we'll get some practice with that also. Alright, the last comment I want to make here is that in practice, circular lists are useful sometimes, but it's more useful to have a list that simply has a beginning and an end. And so what we're going to do is the last node of the list, where is it going to point? If there's nothing else in the list, we're going to have it point to a special location which we use as a key to tell us, hey, this isn't actually the address of the next node. This is our indication that there is no next node. So we're going to store a special value in the last node of the list. And we could pick a value. We can say I'm going to store 99 there. But what if we happen to have a node whose memory address was 99? We might have a node here at location 99. If we put a 99 here, our code would say, oh, that's the end of the list. So we want to put a location here that we know is never going to be an actual valid memory location. And what's the location we can use for that? Location 0. And so we have an object defined inside standard.io.h called null, uppercase N-U-L-L, and it's a pointer to location 0. And so if we set this last pointer to be null, we can use that so that as we move down the list, when we get here, we can print out that data value, and then when we look at next and we see it's null, we'll say, that's it, end of the list. Nothing else to work with here. So some of the practice problems will have you take this code that, we're just moving down the list forever, and instead move down the list until the next field is null, and then at that point we know we're at the end of the list. So you can experiment with that in your practice problems. All right, so this is the high-level view of pointers as they apply to dynamically allocated memory, and in particular how we use that for linked lists. So in the next video, for the next class, we're going to dig more into the linked list idea itself, and we're going to expand this idea of nodes pointing to other nodes, and start looking at how we work with that, how we insert into that, how we search for it, and what the advantages are of doing this over just having a plain old array. And that's going to take us back to our previous lecture on order of complexity, and we're going to see that there's some significant advantages of using a linked list instead of an array once we start trying to do things like insert data into our list. So that'll be a future lecture, but for this one, go ahead and take a look at the practice problems, and then we'll start working with these ideas in class.